Greetings, everyone. In this video, we will be talking about energy and redox and what these two things mean for life. Okay, so we're first going to start off with energy. Now, if you've taken physics, maybe chemistry, you'll probably know about this, but for those of you who don't, and for those of you who just need a reminder, we're first going to start off with the first law of thermodynamics, okay? And this will kind of ease us into energy. Now, the other way you can think of the first law of thermodynamics is the law of conservation of energy. And that is, first off, energy is the ability for something to do work. So essentially, for a system to do work, it must have energy. Notice, though, that the total energy within an isolated system is constant. This means that energy cannot be created nor destroyed, but can be transferred from place to place. Now, let me give you guys an example. What this means is that when we convert, with a heater, okay, a space heater, we're not creating heat, or we're not creating energy in the form of heat. Rather, what we're doing is we're converting electrical energy to thermal energy. We are not creating energy, we're just converting it. And now you might be thinking, but that's crazy to think about. We're always creating energy, from coal or wind power and whatnot. That's all just being converted, right? Wind energy, right, is kinetic energy from the wind that we are harnessing and turning into mechanical energy and stuff like that. That's a lot more physics side, but still I think it's important to understand. And now, in the grand scheme of the universe is a system. So that means all energy in this universe is constant. It can just be transferred around and converted into one another. That's what we mean by total energy within an isolated system is constant. Now, because we are in an isolated system, right, our universe, we can lose energy. We can also gain energy, right, as our own kind of organism. However, the total energy in this system that we are a part of, the universe, remains constant. Okay, so the second law of thermodynamics, this is the other one we need to talk about, is that as energy is transferred or converted, more of it gets wasted, meaning that when we take an electrical energy and convert it into thermal energy, it is not a 100% conversion. Some of that is lost, especially when we talk about like electrical energy to mechanical energy. That is a big issue of some of that energy is lost to heat. Okay, and it's about how do we minimize how much energy is lost to heat. That's very important for making machines more efficient. So how do we measure this essentially loss of energy is through entropy, which is denoted by the sign S. So entropy is the measurement of disorder or randomness within a system. So the more entropy, the more disorder. If you want to think about it in terms of, college students or high school students, your room. I definitely fall victim to this. And by fall victim, I mean it is totally my fault. But my room is, a mess sometimes. The more messy my room, the more entropy in my room. Essentially, it's more chaotic. Okay? So, in an isolated system, so in our universe, entropy will increase over time. Okay? But now you guys should be thinking, well, we're not a physics class. We're not an astrology class. Or, no, astronomy. I know my words. We're not an astronomy class. We're not geologists. We are biologists. So what does entropy mean for life? So this is how the second law of thermodynamics relates to biology, to humans. Notice, living organisms are open systems, meaning they're not closed, meaning that the energy in our system can change. And if we go backwards, so notice isolate, oops, I want to use this color in an isolated system. Entropy will increase over time. Because we are an open system, notice, open, our entropy can decrease. And our energy, right, our ability to do work is not constant. Because we are part of a larger closed system, the universe. So, living organisms can decrease their entropy. However, it's at the expense of increasing the total entropy of the environment in which they exist. So, when living organisms decrease their own entropy, the total amount of entropy in the universe, right, our environment, increases. So there's kind of a trade-off there. We're pretty selfish. We're decreasing our entropy, making things more ordered at the cost of the universe. Wow, how could we do such a thing? But I digress. When there is a decrease in entropy within a system, there is an equal or greater, so notice it can be equal or greater, increase in entropy elsewhere within their surroundings, right? For us, we would just say the universe. So, living organisms resist decay. Okay? Right? We don't just spontaneously decay. Or I guess we kind of do. But we don't just decay. We're still here after many, many years. I'm 20 years old. So we're here. We don't decay. Or we do decay. We just are very, very slow at it. Much slower than we should be. We also grow and reproduce, and we do so in an ordered manner. Cells themselves are very, very ordered and structured. All of that order and structure is at the cost of increasing the entropy in the surrounding area, as in our Earth or the universe. So we decrease in entropy, the Earth increases, or the universe increases in entropy. However, we, I don't want to say this, we become more ordered, right? And that's really important for life, right? Cells are all based off of order, especially your cell membranes. Okay, so now that we understand energy, okay, and with the first and second law, we need to understand reactions. And this is going to get kind of chemical and whatnot, so try to stay with me. If you have a background in chemistry, maybe you've taken a high school honors chemistry, basic chemistry, AP chemistry, or you've taken Chem 2, the Chem 2 series here, this will really, really help you. You've seen all of this before. Okay, the first thing is reactions. Reactions are reversible, meaning that when we combine A and B together to make C and D can combine together to make A and B. Meaning, for this forward reaction, which I will label in yellow, A and B are the reactants, C and D are the products. Now, for the backwards reaction, C and D are the reactants, A and B are the products. Okay? Now, if you leave this going, eventually the system will come to an equilibrium. Let's think about why this is the case. Well, it says that the rate of forward reaction decreases as the concentration of A and B decrease. But that doesn't make any sense to me. Why would that be the case? How I can describe it to you. Let's say in order for a reaction to occur, two people have to run into each other. Okay? So, we have a room full of 100 people. Every time they run into each other, a reaction occurs. And when the reaction occurs, let's say we lose those two people. So, after, let's say, two people hit each other, reaction occurs. Instead of having 100 people, we lose those two, so now we only have 98. Imagine that keeps happening. Eventually, we'll get to a point where we started with 100 people, and we, maybe end at about 50 people. Okay? Think about how likely it is for two people to run into each other when there's 100 people in a room versus 50 people in a room? It's a lot less when it's 50, right? I mean, we have more space to ourselves. We're less likely to run into each other. If it's really, really packed, we're just constantly hitting each other. If we have so much space, we're likely not. So now, at 50, we have so much space, we're not going to hit each other. We're likely not going to have that many more reactions, right? We're not going to have a lot of reactions when compared to 100 people in a room. So now, this first thing makes a lot of sense. The rate of the forward reaction will decrease as the concentrations of the reactants decrease, because it's less likely that they're going to hit each other to have a reaction. Okay, but now let's look at the second thing. The rate of the backward reaction increases as the concentrations of C and D increase. Well, knowing what we just talked about, that makes sense, right? Because as the concentrations of C and D increase, right? That's because A and B is going towards C and D. Well, now there's going to be a lot more C and D in a system. As you increase the amount of C and D, essentially what we're doing is, instead of going this way, we're going this way. We're starting at 50 people and going to 100 people in a room. As we increase the amount of people in a room, we increase the likelihood that they're going to run into each other. And right when we said, when two people run into each other, we get a reaction. So as the concentrations of C and D increase, the backwards reaction rate increase, because when C and D hit each other, they form A and B. So at equilibrium, what happens? Well, essentially we have no net change. This does not mean that A and B are not going to C and D and vice versa. This just means the net change is zero. That's what equilibrium means. Net change is zero. Okay? On the micro scale, on the atomic scale, things are changing, right? A and B are going to C and D. But that forward reaction rate is equal to the backwards reaction rate. Okay? So the reactions are still occurring at equal rates, and concentration of reactants and products remain constant. So on the micro level, on the macro level, there is no change. There is no net change. On the micro level, there is change. It's just balanced out. Okay. So to describe this, we have what's called the rate constant, K. Okay. This is the probability that two molecules will react. Okay. The reaction rate is the number of molecules that react over time, and this depends on the rate constant and concentration of reactants. At equilibrium, Kf is the rate constant of the forward reaction. If we multiply that by the concentrations of A and the concentrations of B, it will be equal to Kb, which is the rate constant for the backwards reaction, times the concentrations of C times the concentration of D. Okay? And so now, if we were to get all the K's on one side and not everything else on the other side, what we end up getting is we'll divide this by Kb, and this side by Kb, and we're going to also divide everything by the concentration of A times the concentration of B, right, to move these guys over. We end up getting Kf, let me write that a little bit better, Kf over Kb is equal to the concentration of C times the concentration of D divided by concentration of A times the concentration of B. Otherwise, we can think of, for the forward reaction, products over reactants. But because our reactions are reversible, we don't like to really say that. We only will say that in chemistry when we're doing a forward reaction. I shouldn't even say that. That's for your Chem 2 class, not here. And we can simplify Kf divided by Kb as Kq. otherwise known as the rate constant, K, for equilibrium. So KEQ is equal to KF over KB, which is the concentration of the products of the forward reaction divided by the reactants of the forward reaction. So remember, this is for the reaction A plus B goes back and forth, C plus D. Okay? So that is the rate constant in reaction rate. Notably though, reactions have an activation threshold, otherwise known as the activation energy. Sometimes you'll see it referred to as AE. Sometimes you'll see it referred to as E sub A. That's why I put both, because you'll see both. So what happens? We have an energy of our kind of molecules. So R stands for reactants, P stands for products. Okay, we have an energy level of those guys, and then time will typically be on the bottom, or progress of reaction, whatever you want to say. So the reactant started at a specific energy level. Notice how it doesn't just go straight down. You have to actually increase the energy. This shows an increase of energy. You'll see it like that. So energy increases as you go up. Okay, so our energy increases. Why? Because that's the amount of energy it took to break the bonds and get everything going towards the products. So we supply energy. This energy difference here is referred to as the activation energy. That is only from here to here. Okay, that is activation energy. At the very top, at the peak here, this is what we refer to as the transition state. It's kind of a middle ground between the reactants and the products. Okay, it's like kind of a hybrid, I guess you can say. It's what we call the transition state. Then what we see a sudden release of energy. And we go down to the energy of the products. The difference in energy from the reactants and the products is referred to as delta G. Do note, delta G does not include activation energy. It only includes the difference from here to here. That is all. Now, as we talked about in the protein section, enzymes will do wonders for reactions by decreasing this amount. Maybe the reaction only needs to go up to here, and then it goes down. Okay, using an enzyme. That's why enzymes and catalysts are so important for biology. Really quickly, is this an exergonic or an endergonic graph? Well, the products have less energy than the reactants, meaning that delta G is negative, right? Because we do delta G is equal to E of the products minus E of the reactants. Energy was released, so that is not the right size. Our reaction shown here is exergonic. You should also be able to draw, an endergonic reaction. So I won't draw that here, but do know how that works, and that's where the energy of the products is more than the energy of the reactants. So it should be about here, right? Actually, I'm going to draw that in a different color, not to confuse anyone. This would be for an endergonic reaction. Okay? So the one I've drawn here, the graph I've drawn here, is exergonic. Okay. Now that we understand energy, we're going to talk about this thing called redox. And what does this mean? Well, it stands for reduction and oxidation. Okay, redox reactions. So, living organisms harvest and use energy by oxidizing fuel. And we'll get into what that means. Redox refers to the coupled chemical process essential metabolism. Essentially, what does coupled mean? It means you will have two reactions that occur simultaneously. You cannot have one without the other. Redox is a coupled reaction. You cannot reduce something without oxidizing something else. That is a law. You are not able to reduce anything without oxidizing something else. Okay? That's just something you gotta know. There's no, I have not come across a single exception to that rule. But what does oxidation and reduction mean? Well, oxidation refers to the loss of electrons. In biology, we tend to look for a loss of hydrogen. Okay? Because when we lose a hydrogen, we'll lose an electron. So, you can refer to this losing electrons or H plus leaving donor. Reduction is the gain of electrons or the gain of hydrogen, right? This is, once again, E minus is electrons. And it's essentially a hydrogen acceptor. You gain hydrogen, that brings you electrons. To remember this, I like to use the acronym OILRIG. It stands for the oxidation is the loss of electrons. Reduction is gain of electrons. Okay? So when I was first learning this stuff, I would just write oil rig at the top of my test and I was done. That's how I did it in high school when I don't know, when I learned this stuff first. Probably a long, long time ago. So, let's do an exercise. We need to figure out which compounds are oxidized and which are reduced. Well, in order to kind of know this, you do have to understand formal charges and stuff like that. And so essentially an element in its elemental state will have a formal charge of 0. No, not a formal charge, an oxidation number. Whew, I know my words. An oxidation number of 0. When it's part of a compound, it won't have an oxidation number of 0. You can typically see, or oxygen will typically have a -2 oxidation number. So we can even write that in -2. Copper, well, we know that the charge on this molecule is 0. So if oxygen has a oxidation number of -2, copper has to have one of +2. Okay? And zinc, well, it's in its elemental form. So it has an oxidation number of 0. But now let's go to our reactant side. Copper is now by itself. It's in its elemental form. So it has an oxidation number of 0. Zinc is part of the molecule, but we don't know what it is because transition metals can kind of be all over the place. But we know oxygen is almost always -2. The only exception is in peroxides and superoxides, but we won't really run into those in this class. That is for your Chem 2 series. Zinc, on the other hand, right, it's going to become this +2. So let's write out oil rig. Oxidation is loss. So it lost electrons. Let's think about it. If you're losing electrons, are you becoming more positive or more negative? Well, normally when we think of loss, we think kind of more negative, right? But remember, electrons are negatively charged. So if we lose a negative, we actually become more positive. So when we lose electrons, when we're oxidized, we'll become more positively charged. Okay, which one becomes positively charged? Well, zinc goes from 0 to 2. So I would say this here, whoops, oh, please don't be like this, is the oxidation. Okay, let's see. Oxygen goes from -2 to -2, so it doesn't change at all. But what about the copper? The copper goes from +2 to 0. It becomes more negative, right? So it gained electrons. So this here, whoops, is the reduction, half reaction. Right, copper gains electrons. It becomes more negative. Notice they are always coupled together. You cannot have an oxidation without a reduction. All right. There are a few more terms we need to go over. So we talked about, okay, what compounds are oxidized? Well, copper is reduced, zinc is oxidized. What about reducing and oxidizing agents? Well, a reducing agent, write it over here, reducing agent is causing something else to be reduced. So if it's causing something else to be reduced, remember, redox is coupled together, it causes something else to be reduced, so it is oxidized itself. So oxidized itself. And the oxidizing agent, well, if it's oxidizing something else, it's being reduced. So reduce itself. Well, it reduces itself, essentially. So, let's see. Oxygen, it's a Brinkelhoff gas. Actually, both of these are Brinkelhoff gases. So they're both in their elemental state. So 0 and 0. In water, oxygen is -2. Hydrogen is +1. Because there's 2 hydrogens, 2 plus 1s, that's a +2, cancels out with the -2. We have a net charge of 0. So, which one becomes oxidized? Well, oxidize, right? Oil rig. Oxidation is the loss of electrons, so it loses electrons, becomes more positive. It looks like here is your oxidation. Let's double check. That makes sense. Oxygen is being reduced because it's gaining electrons. But this question didn't ask which is oxidized and which is reduced. It's asking which one is the oxidizing agent. Well, the oxidizing agent is the one that is reduced. So that means oxygen, O2, is the oxidizing agent. Right? It is oxidizing hydrogen. It's being reduced itself. And that means H2 is the reducing agent because it itself is being oxidized, right? It is reducing oxygen, oxidizing itself. So H2 is the reducing agent. It's causing something else to be reduced. Okay? The final thing is putting this all together with the redox tower. Now, I wasn't able to draw the entire thing, but this is the basics, okay? The redox tower shows us the reduction potentials. So, essentially, it's the tendency of a compound to be reduced. Essentially, how many electron volts, is that E, maybe it's EV? I don't remember. Electron volts. Oh, it's like that. Electron volts you get when something is reduced. And it's given in a half reaction. So, the oxidized form is on the left. The reduced form of the reaction is on the right. See how there is a slash there? CO2 is the oxidized form. Glucose is the reduced form. We can also know that, right? If we were to draw out CO2, versus glucose. Glucose, I'm actually not going to draw it because it's kind of a crazy molecule. See how it has a bunch of H's? This has none. Remember, how do we can tell something's reduced? It has a bunch of hydrogens, right? This guy has more hydrogens than this guy, so it is the reduced form. That's a good way to remember which side is reduced and which side is oxidized. Okay, notice though, good electron donors have very high negative reduction potentials, meaning that glucose is one of the best electron donors, because if you go CO2 to glucose, that is a negative 0.43 volts. This does not mean it produces 0.43 volts. That means it actually requires 0.43 volts. So this is different than like endergonic versus exergonic, right? Exothermic means it produces energy, has a negative delta G. Electron volts work the other way around. If you require electron volts to go, you have a negative. Positive electron volts are more spontaneous. They will occur naturally. They're favored. And so in order to couple two of these things together, the electron voltage should either be 0 or greater than 0. It should be positive. So now, if we go CO2 to glucose, we require 0.43 volts. But if we go glucose to CO2, remember it's the opposite. We're going the other way, so it's a negative 0.43 volts. So that's equal to 0.43 volts. Now we have a positive voltage. So when we oxidize glucose, turn it into CO2, we get a positive voltage that we can then use for other things. Remember, well, actually, you guys probably haven't gone over glycolysis yet, but this is really important for glycolysis, the TCA cycle, and the electron transport chain, which are all part of cellular respiration, and it will come to play also in photosynthesis. So understanding this now is really, really important. Glucose will be oxidized, and we can use O2 as its electron acceptor. Gosh, talking is so difficult. And when we turn oxygen into H2O, we get a positive 0.82 volts out of it. I forgot the voltage there. So essentially what we say is anything that's top right can reduce something that's bottom left. Let's see. I want to write it like this. Essentially a giant arrow. Like that. So if it's above it to the right, it can reduce it. So glucose can reduce 2H+. Glucose can reduce NAD+, and glucose can reduce oxygen. Okay? So it'll act as the reducing agent, right? Because it itself is oxidized, becoming CO2, and it reduces oxygen to H2O. So if these kind of questions come up on a test, you are not supposed to remember them. Don't bother trying to remember all the different voltages and all that stuff. It's not worth it. You will be given a redox tower on a test if you are supposed to know this, okay? And you also have a redox tower in your manuals. You can find it online. I just didn't want to write it all out here because I would be here for an hour trying to write it all out, and it would be incredibly tiny trying to fit it all in this tiny space. So I just drew a very simplified version, but the point still stands. All right, so that is all I have on energy and redox. As always, I really hope your studies are going fantastic. I know you are going to do great in all your classes and in Biz 2A. Like always, if you need extra help, Go to office hours. You can message me on Discord. Use the resources that you have at your disposal. Because why not? You're not having to pay anything extra for them. Might as well use the resources you have. But I know you guys are going to do great. Good luck with your studying for this class and the other classes. Good luck with life in general. I know you all are all super busy, making sure you guys sleep and eat and all that stuff. Take care of yourselves. But yeah, that is all I have for today.